However, we would like to find some conditions under which we can ensure these two are equal, and that is going to be our next theorem. So, theorem says let x and y be non-empty sets and C and D be families of subsets of x and y, such that the whole space X can be represented as a union of elements from that collection C, okay, and the space Y also can be represented as union of elements from that collection D. So, we are putting this condition, this collection C and D are such that there is a sequence of elements of C which gives you the whole space X, and there is a collection of elements from collection of sequence D I in the collection D, such that its union is again equal to Y. Under this condition, we are going to show that the sigma algebra generated by C cross D is same as the sigma algebra generated by C times the sigma algebra generated by D. So, this equality holds. Of course, we have already proved that S of C cross D is a subset of the product sigma algebra S of C times S of D. We only have to prove the other way around inequality. So, what we have to show is the following, namely, so we are given. So, this is the fact which is given, that x can be written as union of C I equal to 1 to n, where C i's belong to C, and y also can be written as a union of elements d j equal to 1 to infinity, where d j's belong to D. And these two conditions we want to show imply that S of C times S of D is equal to S of the sigma algebra generated by C cross D. So, we have already shown that the sigma algebra generated by C cross D is a subset of this. So, only to show, so we have to only show that left hand side, that S of C times S of D is a subset of S of C cross D. So, this is what we have to show. To show this, we will follow the previous proposition, which said that the product sigma algebra is the smallest sigma algebra with respect to which the projection maps are measurable. So, supposing we are able to show that the projection map P is S of C cross D measurable, and P of y is also S of C cross D measurable. So, if we show this, then what will mean? So, P x and P y are both measurable with respect to this sigma algebra S of C cross D. So, it must include the product sigma algebra, namely S of C cross S of D. So, let us show that these two maps are measurable with respect to the sigma algebra S of C cross D. So, for that, so what we have to show is the following. So, let us look at the case of the projection map P x. So, P x is a map from x cross y to x, and here we have the product sigma algebra S of C times S of D, okay, that is the product sigma algebra. On x we have the sigma algebra S of C. So, what we want to show is that that P x is in fact measurable with respect to the sigma algebra S of C times S of D. So, P x is measurable. This is what we want to show. So, to show that, let us take a set. So, what we have to show this? We have to show that for every set, say A belonging to S of C, should imply that P x inverse of A belongs to S of C cross D. So, that is what we have to show. So, let us first observe what is P x inverse of A. If A is a subset of x, if A is a subset of x and belonging to, so let us not bother at present where it belongs. So, let us look at P x inverse of A, that is going to be equal to A cross y by definition, because A is a subset of X. So, the projection lies in A, that means the inverse image is A cross y. And now, by the given condition, the set Y is representable as a union. So, this is A cross union of d j's, j belonging to 1 to infinity, where each d j belongs to the collection D. So, that means I can write this as union j equal to 1 to infinity of A cross d j. Okay. So, this implies that P x inverse of A is written as union of rectangles which look like A cross d j. Now, d j's are inside the sigma algebra, inside the collection D, and if A belongs to C, then this will belong to C cross D. So, and the union, so that will mean that, so the union will belong to the sigma algebra generated by C cross D. Why? Because A cross d j will belong to C cross D if A belongs to C. So, if A belongs to C, then P x inverse of A, just now represented as this, belongs to C cross D. So, but what we want to show is not only for C, for S of C also this property is true. So, we apply the usual sigma algebra technique to prove this. So, let us write U to be the collection of all the subsets A belonging to S of C, such that P x inverse of A belongs to S of C, S of C times, so belongs to S of C times D. So, let us look at this collection. So, what we have proved just now, so we know that C is contained in U, okay, and U is a collection of subsets of S of C. So, that is contained in S of C. But what we want for every set A in S of C, P x inverse of A belongs to S of C. That means, we want to show that this collection U is actually equal to S of C, and U is a subset of S of C and C is inside U. To show that U is equal to S of C, it is enough to show that the collection U is a. So, to show that U is equal to S of C, it is enough to show, so enough that U is a sigma algebra, because once you use a sigma algebra, it includes C. So, the smallest one, that is S of C, will come inside. So, everything will become equal. So, we have to only show that this is a sigma algebra. So, let us look at empty set belongs to U, because it is just look at it is just empty set is equal to P x inverse of empty set. Okay. So, empty set belongs to U. And what about x? X is equal to P x inverse of y, and y belongs to S of C cross y belongs to S of C. So, this also belongs to, so because y belongs to okay, P x, we want to show that the whole space A belongs to S of C. So, what we want to show is that x belongs to. So, look at P x inverse of if we look at P x inverse of x, that is x cross y, and that belongs to S of C cross D. So, that implies x belongs to this collection. So, x is also inside it. So, empty set and the whole space belong to it obviously. Let us look at the second condition, that if A belongs to U, then that implies P x inverse of A belongs to S of C cross D. So, that is given to us, but S of C cross D is a sigma algebra. So, it is closed under complements. So, that implies that P x inverse of A complement also belongs to S of C cross D. But P x inverse of A complement is nothing but, so that implies this set is nothing but P x inverse of A and complement of that. So, that belongs to S of C cross D, and that implies that A complement. So, that means that A complement belongs to U, because it should be other way around. P x inverse of A, P x inverse of A belongs, that means this complement belongs to S C cross D. So, if a set belongs, its complement belongs, and this is nothing but the complement of P x inverse of A complement. So, whenever a set has the property that P x inverse of A belongs to the sigma algebra, P x inverse of A complement also belongs to the sigma algebra S cross C cross D. That means A complement belong. So, U is closed under complements, and finally, let us look at, suppose AI's belong to U. For a sequence I bigger than or equal to 1 belongs to U, that means P x inverse of AI's belong to the sigma algebra S of C cross D. So, these are usual techniques for proving a sigma algebra. So, that implies, and this is a sigma algebra S of C cross D, and P x inverse of AI's belong to it. So, a union of them, P x inverse of AI's, their union 1 to infinity also belongs to S of C cross D. But this union of the inverse image is inverse image of the union. So, that is P x inverse of the union I 1 to infinity. So, that belongs to S of C cross D. That means, we have shown whenever P x inverse of A i's belong to the sigma algebra, the P x inverse of the union also belong. So, that means implies that the union A i's 1 to infinity also belong to U. So, that proves that U is a sigma algebra of subsets of X. So, U is a sigma algebra, includes C. So, U is equal to S of C. That means, P x inverse of A is measurable. So, what we have shown is that if we look at the map P x, x cross y to x, then it is S of C cross D measurable, and the product sigma algebra S of C cross S of D is the smallest one with respect to this is measurable. So, that will prove that S of C cross D includes the sigma algebra S of C times S of D. So, that is how we prove that whenever the families C and D have the property that you can write. So, whenever X is a union of C i's and Y is a union of D j's, where C i's in C and D j's in C, whenever this property is true, then whether you take the classes C and D and take the rectangles and generate the sigma algebra, that is going to be same as generating the sigma algebras first and then taking the product sigma algebra. So, this is a useful theorem which gives us a dividend, namely the following. So, we look at a consequence of this, which says that, so we have this is just a repetition of what the ideas that I have said. To show that P x inverse is measurable, we have to show this, and that can be written as P x inverse of C, because Y is a countable union. So, you write this as a union. So, and the union splits into this union of C cross D j's, and if C belongs to C, so then this belongs, because this belongs to C cross D, which is in its S of D, C cross D. So, P x inverse of C is an element in S of C cross D whenever C belongs to C. So, P x inverse of C is in S of C cross D for every C. So, to prove it is for all S of elements of S of C, this property is true. We use the sigma algebra technique, namely look at the set U, which is a collection of all the sets in S of C which have this property, and then show that we already know that C is inside U and U is inside S of C. So, to prove the equality, one just has to show that U is a sigma algebra. So, that is easy, we have just now shown it is a sigma algebra. So, that proves the fact that whenever C and D are there, two classes of subsets of x cross y, then S of C cross D is same as S of C times S of D. As a consequence of this, let us prove the fact that on the plane B R 2, that is the sigma algebra generated by Borel subsets of R 2 is equal to the Borel sigma algebra of R times the Borel sigma algebra of R. So, to prove this fact, let us just observe the following, namely, so on the real line we have got U, the collection of open sets, and B R 2 B of R, the Borel sigma algebra of R is nothing but the sigma algebra generated by open subsets of real line. So, let us look at the set R 2. On R 2, we have got the collection of the collection of open sets. So, and the sigma algebra generated by them. So, let us write U of R 2, the collection of open subsets of R 2, and generate the sigma algebra. So, B of R 2 is the sigma algebra generated by open subsets of R 2. So, whatever we are claiming is the following. Look at the Borel sigma algebra of R and look at the product of this with the Borel sigma algebra of R. So, that gives you the sigma algebra of subsets of R 2, and on the other hand you have got the sigma algebra of subsets of R 2 called the Borel sigma algebra of subsets of R 2, and what we want to show is that these two are equal. So, note on the left hand side, so B of R cross B of R is nothing but the sigma algebra generated by open sets, right, times the sigma algebra, again the same sigma algebra S of U. So, it is the product of the same sigma algebra with itself, the Borel sigma algebra with itself, and the Borel sigma algebra is generated by open subsets of the real line. So, this is a perfect setting for applying our previous theorem. So, we have got x equal to R equal to y and C equal to D equal to open sets. So, if we look at, so that implies, so our previous theorem will imply that if we look at C cross D, so if we look at U cross U, okay, and then look at the sigma algebra generated by it, that must be equal to the sigma algebra generated by that must be equal to the sigma algebra B r cross B r cross B r, right. So, that is from our previous theorem, but what we want to observe here is that if you look at U cross U, okay. So, if you look at the sets of the type U cross U, then these are sets of the type. So, what is the set in the type U cross U? So, that is the sets of the type an open set U 1 cross an open set U 2. So, these are the type of sets which belong to U cross. So, U 1 and U 2 both open. And now, if you take any open set, say E, any open set in R 2, then this is effect from the basic metric spaces on metric spaces, that the open sets in R 2, okay, the sets of the type U 1 cross U 2 form a base for the topology of open sets for the topology of R 2. So, what we are saying is, if we, then this implies that E can be written as a countable union of sets E i's 1 to infinity where each E I is a set belongs to U cross U. So, this fact is from basic topology, namely R 2 is second countable and the sets U 1 cross U 2 form a base for open sets in R 2. So, this together imply that every open set in R 2 can be written as a countable union of sets E I, and these E I's are open rectangles, you can call them. Each E I is a open set cross another open set. So, by that fact, that will follow that the sigma algebra S of U cross U is same as the sigma algebra on R 2 generated by open sets, and that is B of R 2. So, that will prove that the Borel sigma algebra in R 2. So, that will prove that the Borel sigma algebra in R 2 is same as. So, if you want to generate Borel subsets in R 2, what you can do is you can generate Borel subsets in real line and then take the product sigma algebra Borel subsets cross Borel subsets, and that will give you the product of the sigma algebra of Borel subsets in R 2. So, with that we come to the conclusion of the description of sigma algebras, products of sigma algebras on R 2. So, the main thing is to remember is the following, namely given x and given y, we can have the product set x cross y. Here we have got a sigma algebra A, here we have got a sigma algebra B. So, if we take sets A in A and B in B, so that gives us sets of the type A cross B. So, these kind of sets are called measurable rectangles. So, sets are equal to A cross B, where A belongs to A and B belongs to B, give you subsets of x cross y. So, they are called rectangles in x cross y, and in general these rectangles do not form. So, R is not a sigma algebra. In general, it is not a sigma algebra. So, you can generate the sigma algebra out of these rectangles, and that is denoted by A times B. So, this is called the product sigma algebra. So, the product sigma algebra is the sigma algebra generated by all rectangles. And another way of generating product sigma algebras is by generating the sigma algebras. So, that we looked at. So, here is x, here is y, there is a collection C here, there is a collection D here. So, we get C cross D, a collection of subsets is a collection of subsets of x cross y. So, one can generate the sigma algebra by this collection. On the other hand, one can generate first the sigma algebra S of C here and generate the sigma algebra by this S of D here, and then look at the product of them. So, these two are equal if we can write x as union of C i's belonging to C, and y can be written as union of d j's belonging to D. So, under these conditions these two are equal, and if this condition is not true, then only you can say it is the left hand side is a subset of the right hand side. So, these are the product sigma algebras. So, what we want to do next in the next lecture is the following. So, here is the set x, here is the set x, here is the set y. So, this is a subset E in the product sigma algebra. So, what we want to do is that for so this if we have got a notion of size of sets A in the sigma algebra A belonging to A, and a notion of size for sets B B belonging to B, we want to know what could be what are the sets for which E contained in x cross y, for which we can define the notion of size. So, in a sense what we are trying to do is that we will try to construct a measure on the product of the sigma algebras A cross by looking at the measures on x and on y. So, we will do that in the next lecture. So, in the next lecture we will look at measures on the product spaces, how to construct given a measure on the space x on a sigma algebra A and a measure nu on the sigma algebra B of subsets of y, how to construct a measure in a natural way on the product sigma algebra A times B. That will also generate generalize the notion of areas in R 2 and volume in R 3 and so on. So, we will continue this study of construction of measures on product spaces in our next lecture. Thank you.